Okay, so we're here again. Before I start, I hope everybody's celebrating the first palindrome day of 2024. Actually, there are going to be a whole bunch of them as long as it's in the 20s. So that's anyway. Besides that, are there any questions? Again, for those of you online, I can't, the way the projection thing works here, I can't really see the chat. So if you have a question, just unmute yourself and speak up. But so far, everything is crystal clear, right? Okay, so today we're going to talk about how to get some information out of our simulation. Just sort of in a basically, why do this all in the first place? And you said, well, because they made me take this class. Okay, well, there's that. That's why you have to do it here. But what out there. So why are we talking about these discrete event models? Because they have proven to be useful in certain situations. But the thing is that it's important to to understand that neither these types of simulations nor any other types of simulations are ever an end in themselves. In fact, if you're part of a study or a project that begins with the purpose of this is to simulate the XYZ, then that should be an immediate red flag, because that should never be the purpose. And simulation models, like all models, are never ends in themselves. They're a means to an end. These particular discrete event models that we talk about here are for analysis, as I talked about in the first class. And so the purpose is to find out something that you don't know, find out an answer to a question that you don't know. Because if you know the answer, then you're just wasting time and money performing a simulation. Now, unfortunately, the way it's often used, and this is really unfortunate, is to simply confirm somebody's predetermined outcome. And what's bad about that is that the result is predetermined. In other words, if your simulation or your model comes up with an answer that is different from what they want, then you have to go back and keep running the model until you tell them what they wanted to know. That is not a good use of models. I mean, you're not supporting a decision maker. The decision maker's already made up their mind, and so you're just giving them some items to put on to justify their predetermined decision. And I hope it should be clear that that's not the ideal way to go about making decisions. In other words, your opinion about it is ideally modified in the face of evidence. And as humans, we're not very good about that. I used to smoke, and I read so much about the dangers of smoking that I gave up reading. Okay, so today we're going to talk about the types of averages, and some of you have had statistics, and some of you are having statistics right now. And whether you have or haven't, you know what averages are. Some of you, your parents may remember Lake Wobegon, where all the children are above average. Anyway, but in our discrete event models, there are actually two types of averages that we have to deal with. One is the tally average, which is the one that you're used to. We're going to call it a tally to distinguish it from a time-varying average. And then it turns out that there's a fascinating relationship between these two in certain types of systems, and that's called Little's formula. And that's actually kind of an amazing, that's one of my favorite little results. And as you may have discerned by now, your instructor has some very weird things going on. But hey, that's between me and my therapist. So, okay, types of averages. First of all, tallies, as we mentioned, that this is what we normally mean by quote an average or a mean, and probably in a statistics context, it is important to distinguish average from mean. I don't know if they've made that distinction. An average is something which comes from data, whereas a mean is something of the population that you're trying to estimate. So, now in practice, it just, they get a little blurred. And here, because we're simulating, everything is going to be an average. So I'll use mean and average more or less interchangeably. And the reason for that is that we don't know what it is we're trying to, we don't know the value, So in other words, the average, and we'll see several types of these by example, is something that you just don't know. There's no formula for it in our simulation models for the actual no kidding mean. Yeah, even though there is one, there always is one. Whether it may even be infinite, but there's always mean. But most of the time we don't know what it is. So so tally, add them up, divide. But time varying, as we pointed out yesterday, these are typically with continuous observations, and really the ideal thing, that whether the discrete event state trajectories or just any arbitrary function, the average of an arbitrary function is typically defined by the area under the curve divided by the x-axis, which in our case is going to be time. Okay, so yesterday we were the event list, and just if it is, I think it's been posted already. There's a written assignment where I'm going to ask you to be the event list for a little bit of a longer thing, and also extract some of these statistics that we're going to be talking about here. But the outcome of all that were these three state trajectories for Q, S, and L. Number in Q, number of available servers, and then L, which was derived from the other two. And these are the data for the state trajectory. So here over time, you notice the time in a discrete event simulation does not move at constant increments. It moves in jumps. So here it jumped from 0 to 2.1, and then it's sort of stuck at 2.1 for one iteration. That sometimes happens. And then it jumped to 3.5, then 4.3, stayed there for a little bit, and then we ended at a time 5.6. So we could have gone on, but I think hopefully you got the idea of how to do that. Okay, so now what we want to do is the state trajectories in themselves are the raw data. So how do we extract things that were of interest of this? Well, things that we might be interested in are what is the, and we're going to focus on average. I know that last time we mentioned sort of maximum, and those are important too. But we're going to focus on averages here. So what is the average number in the queue, for example? What is the average? Well, what is the average number of available servers? But a more useful metric is what is the average utilization overall servers. And then finally, since we have the number in the system, what is the average number that were in the system? So, okay, so those are two values that we want to have. If we were to graph our state trajectories, they look like this. So the number in the queue, if you remember, it kind of stayed constant, and then around here it popped up, but then it immediately popped back down with 0 time. Then it popped up and then stayed there a little bit and then went back down. Whereas the number of available servers, it started at 1, dipped down to 0, and then popped up instantaneously, and then at the end it finished at a value 1, but it didn't spend any time in that as far as we're concerned. And if we graph the number in the system, that's a little more of an interesting one. When the first guy showed up, it popped up to 1. Bless you. The second guy popped up to 2, then it went back to 1, and then down. And especially with this number in the system, it should be fairly clear that a tally is not going to really cut it here. Why? Because, what are the values? We got 0, we got 1, we got 2, and we got another 1, and then we have 0 again. But it's like we add those up and divide. Just intuitively, it shouldn't feel right. In fact, it turns out that we need to weight the amount of time we spend in each of these states, and the absolutely appropriate way to do that is simply the area under the curve. And that's true regardless of what type of function it is. If we have a continuous function, which wouldn't be a discrete event state, then that's also how you do it. And that's kind of what that's about. Yes. Okay, the question is there any merit to discounting the time until the first person shows up? Maybe, maybe not. That's something that you could, that's kind of a decision. In some forms of this, they don't even start the model until the first guy shows up. In practice, in most of the cases for this, we're going to be looking at this is kind of way toward the end of the course. We're going to be looking at steady state types of things. I mean, steady state, what happens at the beginning is not relevant. But if we're looking at transient types of things, that might matter. Again, but for these purposes, we're just going to consider all of the data. So that's what we're after now. Now here's sort of a problem. Like, how do you compute this? Given that you're going to be, now we can compute it by hand when we look at all the data. We actually have to, but when it's running, then actually you may have been thinking, well, maybe we can poll it periodically to see what the value is. And whenever in a discrete event context, whenever a polling concept comes up, that should be an immediate red flag if you're doing it wrong. Okay. Because the thing is that all we need to keep track of is a running total. And because the states change at every time, here's the other nice thing, is that every time a state changes, we can update by what the cumulative or the incremental amount was. And in this case, it's always going to be a rectangle. So now, strictly speaking, this is what the formulas look like. So the area under curve is an integral. And so the average number in Q is, so if Q over T, that would be the state trajectory. That would be the integral from 0 to whatever time we have, divided by the whatever time. And similarly for the number of available servers and the average number in the system. And so, so that's why we made you take a calculus refresher if you hadn't had it already. But the good news is that we don't have to do any calculus here. Why? Because the worst formula of a function that we're going to have to deal with is a constant. And so, so the idea here is at this. Every time there's an event, we can update our running total, our running area under the curve, by the previous state times the time since the last event, which is the previous state times the current sim time now minus the sim time of the last event. Now, in case that's not completely clear, what I'm going to do is let's actually kind of do this. So what I'm going to do is I'm going to copy this, and we'll try to use our cute little whiteboard. Oops, so thing is that, no, that's just the little building. All right, so let's see if we can make this work. All right, so here's our data. I hope, can everybody see that okay? Can I actually? All right, and let's, what I want to do is I want to, let's see, 3, and then up to these, and then we'll put it here. All right. So what we want, oh yeah, so their default on this is kind of screwy. So let's, I want you there, and I want you there, and let's have some extra little stuff there. So, so what I want is I want the integral come on. The integral of Q, the integral of S, oops, come on. Paving. And the integral of L. There we go. Okay. So that's what I want to measure. And now, at the beginning, what is the area under the curve? Well, the area is going to be 0. It's always going to start off at 0 because at the very beginning, the area is good. You know, the width of 0 is 0. So, all right. So let's look at what happens at the arrival event. That's at time 2.1. And so to compute the area under the curve for Q, I take the previous value and I add the previous state, which is 0, times the elapsed time, which is 2.1 minus 0.0. And that all comes out to be 0. Similarly, for S, I have the previous cumulative sum plus the previous value, which for S is 1, times the elapsed time, which is 2.1 minus 0, and that is equal to 2.1. And finally, for our number in the system, it's the previous value plus the previous sum plus the previous value times the elapsed time. So at time 2.1, our area under the Q, under the number in Q is 0. The area under the number of available servers is 2.1, and the area under the number in the system is 0. Is still 0. Okay, so now the next one is at time 2.1, we have it as start service. So we do exactly the same thing. The previous value plus the previous sum plus the previous value. Now the previous value for Q is 1, but the elapsed time is 2.1 minus 2.1, and that's still 0. And similarly for S, our previous value is 2.1 plus the previous value was 1, and 2.1 minus 2.1, but that's going to be 0 still. So we still are left with 2.1. And finally, for the number in the system, it's the same thing. We have 0, the previous sum plus the previous value, which is 1 times the elapsed time minus 2.1, and we're still left with 0. Okay, so that's at the start service time. And now let's roll things to the arrival. when it starts to get a little interesting. Although, so for the Q, we have the previous sum plus the previous value, which is 0, times, in this case, 3.5 minus 2.1. And that's still 0. We're spinning on that, but that's okay. For S, okay, our previous value, and we're still at 2.1. And now for the number in the system, so we have the previous sum plus the previous value times 3.5 minus 2.1, which is the elapsed time, and that comes out to 1 times 1.4, I believe. Okay, so that is at the arrival. I'm sorry, at the, yeah, that's at the second arrival at time 3.5. Now let's look at, so the next one is at end service at time 4.3. So we have at end service, so for Q, we have the previous sum plus the previous value, which is 1, times the elapsed time, 4.3 minus 3.5, and now that is going to be 0.8, I think. Yes. And for the number for available servers, this is at the end service event, we have 2.1 plus the previous value, which is 0, times the elapsed time, 4.3 minus 3.5, and that's still 2.1. And then for our, now, okay, for our number in the system, we have the previous value, 1.4, plus, now our previous value for L is 2 times the elapsed time, which is 4.3 minus 3.5, and that is 1.2 times that 1.6, and I think that's 3. Let me double check that again. And I'm doing the math here without a calculator. So, okay, 2 times 0.8 is 1.6. Okay, yeah. Okay, and we're almost done. But now, one thing I hope you're noticing is just like when we were being the event list, we're not thinking. What do I mean by that? I mean, we're just executing, and when we're executing an algorithm, we're not thinking. And that is the ideal place to be because thinking is hard and hurts. So, yeah. Okay, so where are we? Okay, well, now we're at the start service event. We're at the start service event, the second one. So we have the previous sum plus the previous value, which is 1, times the elapsed time, which is 4.3 minus 4.3, and that's still 0.8. For S, we have our previous sum plus the previous value, which is 1, times the elapsed time, and that's still, we're stuck at 2.1. And then finally, for the number in the system, we have the previous value plus the previous sum plus the previous value times the elapsed time. And that's still 3. And then now we're finally at the last event in our model, and that is at our end service event. So we have our previous sum for Q plus the previous value, which was 0, times the elapsed time, which is 5.6 minus 4.3. And so that keeps us at 0.8. For the number of available servers, we have our previous value, previous sum, plus the previous state times the elapsed time. And the 0 kills that. So we're still at 2.1. And finally, for the number, we have 3.0 plus the previous value, which is 1 in this case, times 5.6 minus 4.3. And say 5, that is 1.3. So this, do I get 4.3 here? Okay, so finally, when we're finally there, our area under the curve when we finished was 0.8 for the number in the queue, 2.1 for the number of available servers, and 4.3 for the number in the system. And so now we can actually compute our averages. Let's see. Let's do a little bigger. Okay, so our average number in the queue is going to be it's going to be the area under the curve over the finished time, which is 5.6. I'm just going to leave it at that. The average for S is going to be 2.1 over 5.6. And similarly, the average for the number in the system is 4.3 over 5.6 again. All right. Okay, and that's surely fascinating. However, there's something interesting that happens here. And that is, okay, those are the time-varying average, but there are also some other things that we're interested in. One is, what is the average amount of time the customer has actually spent in the queue? If you're the customer, that's kind of more of interest to you than it is to the system. I mean, and even for those running the system, that's something that you're sort of concerned about, because the longer that is, the more customers are going to be unsatisfied and they're not going to come back anymore. You know, just like that restaurant that nobody goes to anymore because it's too crowded. You know that one. Okay, so so how can we figure out, though? How can we calculate that? Well, what's interesting here is that even though we can easily compute these time averages, we cannot easily compute the tally averages that we're interested in. Why? Because in order to do that, we need the entire state trajectory. Whereas I hope you notice that in computing these averages, all I needed to know was the running total, the amount of elapsed time, and the previous state. I just needed those 3 values. I didn't need the entire state trajectory. But to compute the tally averages that we're interested in does require that. So, but given that we have the entire state trajectory, we can kind of look at it and compute that. So let's look at this first guy. The first guy showed up at time 2.1, and he left at time 4.3. Let's make you red just so we can see you better. Okay. And the second guy came at time 3.5 and left at time 5.6. So how much time did they spend in the system? So that's a quantity that's often called W, and that would be, the first guy was 3.5 minus 2.1. That's the first guy. And then the second guy was, he left at time 5.6 and showed up at time 3.5. And so we have 2 observations. We divide that by there, and what do we get? We get, okay, what is this? This is 1.4, and this is 0.8. So let's see. wait. It's 1.4 at 5.0. What is this? That is 2.1 and 1.4. So that is equal to 4.3 over 2. How do I move this? How do you move these little things?
It should be 3.5 over 2, shouldn't it?
Well, let's see. Okay, this is 1.4. Oops. And then this one is 2. Why do you hide that?
For the first one, shouldn't it start at 4.3? 4.3 minus 2.1?
Should it start at 4.3? Oh, well, when did the second guy arrive?
Oh, okay, 3.5.
Yeah, he showed up at the, so so I mean, if you're yeah, he showed up at 3.5. You left at 5.6, and so that would be 2.1. That's correct. The first person did leave then, but we're, this is most annoying. This is 3.5. Is that 1. Wait, rival. Oh no, yeah. This he left at 4.3. Yeah, you're correct. So that should have been 2.2. So 2.2 and 2.1 is 4.3. Okay. And okay, so now here something kind of interesting happens. There's another metric, which is the average arrival rate. And that is the number of arrivals divided by the time. So in this particular case, how many arrivals did we have between time 0 and time 5.6? We had 2, right? And so our average arrival rate would be 2 over 5.6. That's something that's often called lambda. Now, here's the interesting thing, is that, and here, now is this going to let me save the whiteboard? I'm probably going to lose all this when I save it, but well, we'll see. Okay, so let's go back here and talk about Little's formula. Okay, so the tally averages are just kind of what we did. And then this is kind of what we, more or less what we came up with. Yeah, I'll get back to, yeah, utilization is kind of another one that's of interest. If you remember, our sum, our area under the curve for the number of available servers was 2.1. The time was 5.6. There was 1 server. And when we take 1 minus that, that gives the utilization. In other words, the average utilization per server is what that is. But let's see, now this is where I kind of did it beforehand. And as opposed to kind of doing it live. This is My screen sharing is paused. Can you remote people see the screen share?
Not currently, no.
You can't. What about now?
You
Can
see
you
it
see
now,
it
sir?
now? Yep. Okay, so here are the actual computations, so the first customer showed up at time 2.1. He started service at time 2.1, and then so he was in the queue for no time units. He started service, he ended service at time 4.3, and so his time in the system was 2.2. Second one arrived at time 3.5. The time in the queue was 0.8, and he or she ended service at time 5.6, and so was in the system for 2.1 time units. And so for each of, so here's customer 1, customer 2. And so the average delay in the queue was 0.8/2. And the average time in the system was 4.3/2, so these are tally ones. Notice we had to look at the entire state trajectory to figure that out. Now, here's the fun thing. If your definition of fun is as weird as your instructors. Okay, so for this particular system, and it turns out, and this is true for any kind of system in which you have entities, just things that come into the system, stay in the system for a while, and then leave the system. It turns out that if you look at the same metrics, if you look at the average number in the system, because if they come in the system and stay for a while, there's going to be some time average of that. If you look at the average time that they spend in that system, which was going to be a tally-like thing for each individual one, and then if you look at the average arrival rate to the system, which in our case is going to be just the number who arrived divided by, however time it is, then it turns out, interestingly enough, that when the system is empty, why are United? This is sort of weird. I can't see it on my computer. I have to kind of do it here. When the system is empty, then this relationship exactly holds. Exactly. And this is not very intuitive. And although this is something that the people who've kind of worked with these models have known probably for about 100 years or more. Again, going back to Erlang, who worked on these types of things in the early part of the 20th century. So who the heck is Little? Actually, Little is a fairly recent guy who was doing a paper, being an academic, that's kind of what academics do. And he was using this result that everybody knew. Everybody knew this result. I mean, this isn't like, and so being a good academic, he wanted to find a reference to it. Because whenever you use a result, you should always reference it. When you write your master's thesis and you use somebody's result or a quote, you always reference it. He couldn't find a reference. This was something everybody knew, nobody referenced. So he wrote a paper where he put this result in and got his name on it. So Don. What? I think it was like in the 60s or 70s. Don't quote me on that though. But it was in recent times. Not. Okay, now say okay, that's kind of interesting. But the deeper result is this: is that in any system like this, one of two things is going to happen. And one is the system is going to periodically empty out. Periodically, it's just there's going to be nobody in there. Or the system's going to blow up. I think that was somebody mentioned that yesterday, where it's like, well, that's one of the outcomes. It's like they keep coming in, the queue, just the system blows up, meaning you get more and more and more. The interesting thing is this, is that, as I said, Little's formula holds exactly when the system is empty, as long as it's started empty. That's kind of the other caveat. But it holds approximately as t gets bigger, as you run your model longer and longer, it gets closer and closer to being true. In other words, it may not be exactly true, but it can be approximately true. And so what that means is that if you know the arrival rate, which you can do just by counting, and if you know these time averages, and you want to know the tally averages, you actually don't have to compute the tally. You can compute them by using Little's formula. So in our case, let's just sort of verify it. And like the numbers we got, remember that the area under the number in the system was 4.3, and it ended at time 5.6. Lambda, our arrival rate, was 2 over 5.6, and that the average number, the average delay in the system, it was 4.3 over 2. And look at this, the 2's cancel, and we get 4.3 over, this, in other words, this is exact. And likewise, for the number in the queue, the average number in the queue was 0.8 over 5.6, if you remember, that this is the area under the curve. The arrival rate is still 2 over 5.6. But the area under the curve, I'm sorry, the delay in the queue was 0.8, because we had one guy who stayed there for 0 and another guy who stayed there for 0.8. And so likewise, again, this is an exact result. That's why I didn't, the 2's cancel, and then we get an exact result there. Well, it needs to start empty. Yeah. But for a system that periodically empties, at those periodic times when it's empty, it holds exactly. And that's the key to actually kind of quote, we're not going to quote prove it, but you can mathematically prove that for a system that doesn't blow up, that as time goes to infinity, as you run it longer and longer, you get as close, arbitrarily close to the true value, to the relationship holding exactly. Correct. Yeah. Okay, the last little bit is, okay, so we did it for 2 servers, but again, one of the questions that one can ask of a system like this is, what if, I'm sorry, we did it for 1 server, say, well, what if we had another server that had exactly the same data, exactly the same inputs? Well, what about that case? Well, we do exactly the same thing, the only difference is that we are now initializing the number in the available servers to 2. And so, but the logic is all exactly the same. So the arrival just pops that by 1. So now the start service event here, it takes 1 to 0, but now it takes 2 to 1. So that when the second guy shows up, all of a sudden he, intuitively, second guy shows up, he gets a server. And so using exactly the same data, we've actually finished, we've completed serving our customers now in time 4.8 instead of 5.6. And you might notice that what is the difference? The difference of that is the 0.8 time that the first guy, when there was 1 server, one of the customers spent 0.8 time in the queue. In general, there's going to be kind of overlap on that. So, and we can perform exactly the same statistics on these numbers. So in other words, Little's formula is going to hold regardless of of how many servers we have. It was not an anomaly of just having the two servers. So for example, if we're looking at in this case, the delay in the queue, there was no queue because both the customers got served immediately. Now in the system, the time in the system was actually just their service times. The arrival rate now is a little bit smaller because we finished earlier, but for this, that's still the arrival rate. But if we check this, we see that, at least for the number in the system, so we had here it turned out to be 3.5. Check the calculations there, over 4.8. And likewise for this. So in other words, regardless of whether, how many, you see, it holds regardless of what we call our system. If we call our system the whole thing, then it holds. If we call our system just the queue, then as soon as they leave the queue, they're not in that system anymore, but it holds for that as well. And in fact, this holds for any system like that, regardless of what else is going on. They come in, they stay a while, they leave, this relationship holds. And actually, there are even deeper, you can go, this is just the basic form. There are much deeper forms of this that we won't get into. Okay, so now you're going to get to do it yourself. And since as the instructor's prerogative, I did it for just 2 guys, I'm going to ask you to do it for twice as many. And that's what's in the written assignment. Now, what's next are these things called event graphs that I've been maybe alluding to. And kind of why do that? Well, if you remember how the way that we created our model was a lot of words, a lot of verbiage. And as you can imagine, as the model kind of gets bigger, you kind of lose track of what the heck's going on. More to the point, when we look at all those words, we don't get a sense of what that system is doing. And that's where these event graphs come in, because they exploit the fact that the relationship between one event that schedules another event is a bidirectional relationship. And whenever you have a bidirectional relationship, you can create a directed graph. And when I say graph, in that context, it's not the plot of something, right? It's circles and arrows, right? You've encountered those before. So an event graph is literally a directed graph in which the nodes are the events and the arcs or edges are the events that get scheduled from them. And that way, what we can do is once you kind of get oriented toward that, you can kind of look at one of these models as a graph and get a sense of what the event relationships are about and get a sense of what that thing is doing. So this is, anyway, so this is, needless to say, this is something that your instructor likes. So okay, so that is that. And let me check is there any? Okay, so any questions on what we've done so far? So the assignment 1 is, the written assignment 1 is posted a little later this afternoon. Your first computer assignment is going to involve using event graphs, but I haven't told you what an event graph is yet. So tomorrow at 11, in place of the lab, we're going to have a lecture where I'm going to teach you about event graphs, and then in the class is going to be the lab just for tomorrow. And then maybe I'm still trying to figure out the logistics, is that we may do that swap with OR at your 10 o'clock class, maybe. I don't know. I'm still trying to figure that out. Okay. Any questions from the remote folk? Okay, so, yeah, tomorrow at 11 will be the lecture.